pleasure to be here today. And this audience is absolutely incredible. I wasn't really expecting this turnout to have a full house. So I really think that this speaks to the reach of the Chicago Humanities Festival and the type of work we're doing. Who knew that so many people were going to be interested in the color blue? Well, for me, this has been a slight obsession. I've been interested in this color blue from the very beginning of my career. And as a material scientist, I've been interested in the material discovery of it. We'll be getting back to that through the course of this talk, but I think the best place to start is this image right here. I don't know how many of you have been to the Museum of Contemporary Art, but I highly suggest you go. There's a great exhibit on David Bowie, and I actually saw this image here, which is the 1968 Apollo 8 moon landing. And it shows our planet Earth as a blue ball. In fact, this is when, in the 1960s, late 60s, we started calling ourselves the Blue Earth. But I think it bears an uncanny resemblance to this material that you see here on your right, which is a sphere of lapis lazuli. In the same way that we have our Earth surrounded by clouds, a sphere of blue, this lapis lazuli color also has this blue color to it, peppered with this white material. Now, the thing here is this: I don't think that this is by mistake that early man first adopted this material to be able to express himself artistically. And the reason for this is that it's the type of thing that he would see on the daily basis, to be able to mimic the blue colors that he saw in his atmosphere and his water and all around him. But before getting into that and explaining to you how this material relates to all material invention when it comes to the color blue over the past 6 millennia, I wanted to start with what we find today. Because blue absolutely surrounds us. It's part of our everyday experience. Everything from blue jeans that I'm wearing today to blueprints, all manner of industrial products, they all contain blue. And not only that, we've conflated it with a sense of emotion. So you sometimes feel blue. There's artistic periods dedicated to it, such as playing the blues. And even artists have dedicated entire production to the blue color, such as Picasso's Blue Period. Even one artist, Yves Klein, who we'll be returning to at the end of this presentation, deliberately created his own synthetic version of the blue color to be able to describe the boundlessness of the universe and the deep spirituality that he associated with the color blue. And here's the thing, and this is what intrigues me most about this, is that you don't really find blue as part of your natural environment. It's almost entirely a human invention. Let's unpack this a little bit. So when I'm talking about blue in our natural environment, I'm mostly talking about this, the blue of our sky, because the blue of the sky is reflected in the blue of our water, and it's almost entirely a scattering phenomenon, which means that it's not a chemical color. And this scattering effect was first discovered in 1859 by an individual named John Tyndall, a Brit, who at the Royal Institution devised a very simple experiment in which he took this tube of glass that you see right here, he filled it with smoke particles, and he shined a light through it. And what he found is that blue wavelengths scatter more so than any other wavelength. And that's exactly what we see going on in our atmosphere. And it's also something that you probably know extremely well right here, the Chicago bean known as Cloudgate by Anish Kapoor. And he actually understood the smoke and mirrors effect extremely well, that he's harnessing the color blue through the reflectivity of his work of art. I also wanted to show you this, that it was up for a year in Kensington Gardens Sky Mirror, which I think is an absolutely brilliant piece in its own right. Again, looking back toward our Earth and also the piece of lapis lazuli that I showed you. But here's the thing. I was explaining to my daughter, who's in the audience today, she's 11 years old, and I was saying that you really don't find a lot of blue in nature. And she ran upstairs to her room and was very concerned about me saying this because she knew in her rock collection that she had some really prime examples of blue that were coming from nature. And I had to explain to her this, that the blue color that she saw on these things it's exceedingly rare, and that you don't find it readily in the natural environment. And when you do find it, it's difficult to make a pigment out of it. And if you were to crush up these pigments that you see here, they would produce a gray mass instead of a vibrant blue. So human beings have actually had to invent the color blue. And it also means that you can imagine a time period when there was no blue. And in order to be able to understand that, you have to go back around 9,000 years to a point in time when you were just utilizing your natural environment to produce your color palette. Here we have a cave that's in Argentina, and it's showing the type of palette that you would typically find in prehistoric times, one that's produced of orange, yellows, whites, that are extracted from clay materials that you would find just locally. The black you would get from the soot of your fire that would create some of these handprints that you're seeing here. And it doesn't necessarily need to be Argentina that I'm showing. It could be in Lascaux, which is in France. It could be in China, Africa. No matter where you go at this particular time period, you don't actually find the color blue, never blue. It's really when you see the rise of civilization, the first cities, that you see this material here. Lapis lazuli, lapis, the word for stone, lazurds, the Persian for blue. And in particular, what you see is this blue color that's formed from the lazurite mineral. This is a sodium aluminum silicate, forms a zeolite or cage structure, and the sulfur that gives the color is stuck in between that cage. We're going to get back into the chemistry of this a little bit later in the presentation, but suffice it to say, the type of geological conditions that would lead to the production of this blue color are exceedingly rare, to the point that in antiquity, it comes from only one place on Earth as far as we're aware, and that is in the Pamir Mountains in Afghanistan, in the Badakhshan province, and we can even narrow it down to a more narrow area than that, and that's the Kokocha River Valley and the Sarisang mine. And here you can see it today, and this is an actual worker that's mining this material. It's still a productive site today, which speaks to the volumes of material that's coming out of the site. So there are two routes that might have been taken in antiquity to be able to get this material out to the Mediterranean world, where we're going to actually focus the most of this presentation. One of them is a northerly route, but actually we don't have a lot of archaeological evidence for it. So I'm going to be talking about the southerly route. So if you came down from Afghanistan, went to northern Pakistan, and went to some of the early Chalcolithic sites, such as the ones that I'm showing here, you see these anthropomorphic beads of lapis lazuli that are starting to be used, and a lot of debitage from the actual working of the stone. From there, it travels across the Zagros Plain in Iran to northern Iraq, where we find such sites as Tel Brak. And at this time, you don't only get lapis lazuli, but you get a lot of material culture that's being traded in terms of semi-precious stones. This was a vibrant economy, and you see such things as amethyst, carnelian, shell, and a few pieces of lapis lazuli that are introduced into that area at this time. From there, it travels down the Fertile Crescent to pre-dynastic Egypt in Heracleopolis. And not only do you get these small little beads that you're seeing here, but you get actual statuary that are being formed. This one's around 9 centimeters high, but you can imagine it being hewn from a slightly larger piece of stone, which speaks to the fact that they're actually carrying rocks 4,000 incredible miles from Afghanistan to Egypt. Incredible journey. But it's important to keep in mind what it's used for. This individual is Ebi. He was a state administrator of the city Mari in ancient Mesopotamia, and it shows you how lapis lazuli was used. It's used as an inlay of his eyes, and it's almost never crushed up to be produced as a pigment in antiquity, and this is actually a really remarkable finding. And in fact, I scoured the literature looking for the use of lapis lazuli as a pigment because it would be a natural extension of the creativity of human beings to be able to paint using this material. And in fact, I could only find two examples. This statue that is Queen Amos Nefertari comes from the 17th dynasty. It's at the Metropolitan Museum of Art. And this is work that was done by a conservator there named Anne Haywood, who discovered just a tiny little amount of lapis paint that was used on the necklace, probably meant to depict an actual lapis lazuli necklace. On the right over here, you have an even more enigmatic use of lapis lazuli as a couple little fragments of this lazurite mineral that are peppered into this purplish paint layer, and it was probably just by accident. And as far as I know, these are the only two examples that I can find in antiquity of the use of a ground-up pigment. So the question is, in the total crux of this presentation is, what do you find in the archaeological record? And we're going to be talking about going from such materials as glass in the early second millennium to pigment, the most common pigment ever known to human beings, Egyptian blue, which is introduced in the late second millennium BC. Then we're going to talk about how we lose that technology almost entirely in the Roman period, and we have to reinvent it, which is ultramarine, which is actually crushed up lapis lazuli to form this pigment material. And then finally, the modern era, where we actually synthesize materials to be able to satisfy our need to produce this blue color. So the best place to start with glass is actually this wall right here, because it speaks to a larger trend that's taking place in the second millennium, and that is of tribute. This wall right here is from the Temple of Karnak in Egypt, and it shows Tutmosis III, and very descriptively, holding this group of Syrians by their hair and smiting them with their mace, because he had just been on several successive military campaigns to be able to defeat the Syrians. In order to be able to honor these expeditions into Syria, he erected this wall called the Hall of Annals. And on this wall, you have all kinds of material culture from the particular time period. They have silver, gold, pottery, obelisks that he's erected in honor of the god Amun. But I want to concentrate on this area right here, these enigmatic little piles. And if you actually look in real life, if you take a photograph of it, this is what you see today in this carved relief. And we're looking at these two things here. Concentrate, you can look at the hieroglyphs. The hieroglyphs can be translated as the following: Hesbid and Hesbid Ma'a. And loosely translated, that's blue, and then this other thing called true blue. So already we're seeing some sort of material equivalency right here. And archaeologists have used this to say that one of these piles is dark blue glass, and the other one is lapis lazuli. So the synthetic variant of lapis lazuli. And not only do we find it in the hieroglyphs, but we actually find it in the ancient Akkadian language, which was roughly equivalent in time period, but the Mesopotamian language. And what they have is this term called uknukuri, which is lapis lazuli that's coming from the mountain, obviously this location of Afghanistan, and then lapis lazuli that's coming from the kiln, uknusadi. And what exactly were they talking about here in terms of this material equivalency? Probably this. This material was excavated off of the shipwreck called Uluburun, which sank off the southern coast of Turkey in the 14th century BC, and it left behind these very interesting, what they call bun ingots, that share a lot of shape similarities to these right here. And people actually often equate the shape of these materials with the bun ingots that you see here. We'll return to these ingots a little bit later on, but this is the synthetic equivalent of lapis lazuli, the deliberate creation of a man-made material that could be a trade substitute for this material. So to be able to understand lapis lazuli from the kiln, we have to back up a little bit and understand where it comes from. And it comes from this area right here. What we're talking about, again, is around the 3rd millennium when we introduced the first glazed materials. And it's part of this overall global trade of semi-precious stones. Here we have serpentine, lapis lazuli, all would have been traded from various regions around the Middle East. And then sandwiched in between, we have this material called glazed steatite. Steatite is a magnesium silicate mineral, and surrounding it is a glass layer. And this is some of the first man-made materials to be able to mimic semi-precious stones. In fact, we believe that they were the first things to be engineered to be able to create the synthetic variants of this. So where does this come from? Well, it comes out of this milieu of experimentation. We're talking about the rise of metallurgy at this particular time period, where you have high temperatures that are being reached, you're mining mineral ores that have copper in them, and you're mixing them all together. An anthropologist, actually it's a father-daughter team of Martin Matin, who are two Persians who were working at a ceramic factory, came up with this ingenious idea that they were using dung as a fuel to be able to create the earliest smelting furnaces. That dung contains a lot of salt in it. The salt would have been mixed up with copper dross and scale from the production of metals. And you put that in a kiln, heat it up, it vaporizes and coats your quartz material or steat material to create the first glazes. Of course, once you have this initial inspiration to be able to produce this material, you can actually start to harness it and change it, manipulate it in different ways to be able to create a glassy material. And I'm showing you how they did this. We have archaeological evidence that they were using quartz pebbles, and you can tell that because here we have a little glassy material that's attached to a kiln lining, and here we have the pebble. They were using plant ashes that were produced by local desert plants that were halophytic, meaning that they take in salts into their tissues. You burn them, they act as an alkali flux source that will allow you to melt that quartz at a lower temperature than it would otherwise be needed. You have your colorant in terms of these ores, such as azurite or its cousin malachite, both copper carbonates, one blue, the other green. And then you have calcite. They found very early on, if you didn't add calcium carbonate to your mixture, that it would easily dissolve in the environment and you would lose your glass material. So you can imagine molding all this together, making some sort of sandcastle material, and putting it into a mold. And you would take the object out of the mold and let it dry. And during the drying, it would effloresce, which means all those salts and the copper would come to the surface, forming a salt haze, which when you put it into the kiln, fire it, would produce a glass. And here we have an Ushabti from the late period, which is representative of the type of object that would be produced by this method. And here's actually a scanning electron microscope image, which you can see the structure of the type of thing if you were to take a cross-section of this. What we see is the body, which is formed with porosity, these jagged quartz particles, and then you can imagine the salts going out of these pore structures, rising up to the top and forming this dense glass layer right here on firing, which interacts with the available quartz that's on the upper part of the layer, creating your glaze layer. Of course, you can imagine if you add a little bit more flux, you increase the temperature of the kiln just slightly, you get these sort of things. The first glasses. In around 1300 BC, we see the first sustained production of glass. And the technology that's interesting here is not so much that they've brought the kiln up to a higher temperature, they've used a slightly different mixture of the same raw materials that you saw to create the faience, but it's the use of colorants. Here we have oranges, yellows, reds, whites, and this color blue, and it's this color blue that I want to concentrate on here because this is the equivalent of the lapis lazuli. But how did they achieve it? Well, I was very lucky enough during my graduate work to go to the Egyptian western deserts and look for the cobalt colorant that would have been used to create that deep dark blue color. And to give you a little bit of a context here, this is the ancient capital of Egypt, of Luxor. I've already mentioned the site of Tel Amarna, where we found that piece of quartz pebble, and we're going to absolute middle of nowhere, the Dakhla Oasis. And even today, as an antiquity, there was essentially only a couple little settlements there that would have been able to service the rest of the Egyptian Nile River. Well, where we're going to is this site right here, which is called Qasr Lebka in the Cargo Oasis, and we're looking for this material, an aluminum sulfate. This aluminum sulfate is very special because it contains a fair amount of cobalt and also these other trace elements that we'll come back to. The only problem with the sulfate is that it doesn't mix well with a glass melt. In fact, it's immiscible, which means that they'll separate out from one another. So you actually have to use another material, natron. Natron you know from mummification to dry out the body so it's prepared and preserved for a longer period of time. These are both water soluble. If you put them in a solution, mix these two solutions together, you get a solid precipitate that's formed by this reaction right here, where you formed a cobalt aluminum hydroxide, which you can then harvest and then introduce to your glass. And that's exactly what my colleague Andrew Shortland did in his laboratories in the UK, where he took this sand material, he took some alkali, this cobalt material, and produced this really very deep dark blue colored glass. Too deep in color because he used too much of this cobalt material to be able to make it. This is going to be the only plot that I show you in here, so bear with me. The cobalt here, and I'm showing you this for a real reason, the cobalt is correlated with these trace elements. And what I mean by a correlation is that they lie in a straight line. And when you see a correlation like that in compositional analysis, it means that all these materials, all these glasses that we analyzed are coming from the same exact area in terms of the mineral resources. So what we are showing here is that all the cobalt ore that was used in antiquity for the production of Egyptian glass was coming from this single ore. And we can actually use this to start tracing glass around the Mediterranean. So we look toward ancient Greece, the Mycenaean Greece, and we were able to analyze these beads. And these beads, again, followed right on this line, which means that the same cobalt ore is used to be able to produce these glasses. We look at the Uluburun ingots, and this is work that's done by a colleague of mine, Caroline Jackson, who did the analysis and again found that those points lie directly on this line, suggesting that it's produced from the same cobalt ore. And we can start to look at other material culture. Akhenaten, you probably know this person, known as a heretic king. He actually was very important for the entire history of Egypt because he went from polytheism to monotheism. He moved his capital, and he absolutely changed Egyptian art forever by making it more naturalistic. And along the way, he invented some new materials as well, or at least his workmen did. And what he created in this particular case is this cobalt aluminate. And this is very interesting because the modern pigment made of a cobalt aluminate doesn't appear until 1800 AD. We'll return to this a little bit later. He took his cobalt hydroxide, he fired it to a high temperature, creating this baby blue sort of pigment, and he actually created this entire form of pottery. If you see this, it's known as palace ware, and it's confined to a very short period of time during Akhenaten's reign. And it has the same trace elements as we see coming on from the glasses, which means, again, it's the same cobalt ore source. And for many years, we thought that this was the only cobalt ore source that was used in antiquity, so all the blue-colored glass was coming from Egyptian production. But then we discovered something. We went to the University of Pennsylvania Museum, and we found this material right here. And this, I actually think, is lapis lazuli from the kiln, because this is a chunk of lapis lazuli right here, and I think that they're the visual equivalent with one another because it's peppered with this white material, veined, has the same exact hue. This is truly, truly lapis lazuli from the kiln. And we did analysis of it, and what we found is that didn't match with what our known expectations were. There's another ore source out there. We don't know exactly where it is. It's probably located in Mesopotamia because this is a Mesopotamian glass. And it suggests that this was a global phenomenon. It wasn't controlled by one place. It was actually used by many different people to be able to produce this synthetic variant of glass. But so far, what I've talked about is the synthetic equivalent to lapis lazuli, and it was used as that, as inlay to other objects. But what we really want to see is the way to express yourself naturalistically by being able to paint with the material. And you really need a pigment to be able to do this. To be able to understand the use of pigments in antiquity, and specifically blue ones, you have to go back to periods where there's a little bit of an ambiguity. This is an object that's in the Museum of Fine Arts. It dates back again to the 3rd millennium BC, and it's inscribed to the Scorpion King, and this is the actual inscription that you see here. The Scorpion King brought Egypt together for the first time, started the dynastic system, and inside this little inscription area, according to the archaeological reports, is a blue frit that was added. Now, this is the only photograph that I could find, and when I contacted the Museum of Fine Arts, they said that they were actually actively looking at this to be able to determine whether this was the first blue frit that was actually used. If it is indeed ends up being the case that this is Egyptian blue pigment, it's before there is even a word for blue, which means that the entire material discovery of it is intimately related to the intellectual adventure that man has in terms of trying to figure out what is the word, what is the material, how do I relate to that, and how do we move forward in terms of material design. What we do know is that by the Middle Kingdom, around 2500 BC, we actually get the first sustained production of Egyptian blue, and then from there, it takes off at the same time period in the 1300 BC when we have the first sustained use of glass. In fact, you use the same raw ingredients as glass, and we made some of this material in the laboratory. We took this raw material that you see here, which is a mixture of plant ashes, copper colorant, quartz. We fired it around 900 degrees Celsius, and we produced this blue frit. And it looks exactly like what we find in the archaeological record. And this is a piece of ceramic, and inside the ceramic we have these blue balls that would have been able to be more easily pried out to be able to crush it and produce your blue pigment. If you were actually to create a cross-section of one of these pigment particles, you would get this sort of thing. This is another scanning electron microscope backscatter image in which we see residual quartz particles, we find glass, and we find these laths of what they call cuprorivate. And cuprorivate gives the deep dark blue color to this, and they actually grow out of the glass during cooling. We'll come back to why these things are so special other than their color in the next couple slides. But what this really leads into is a huge new way to express yourself. Not only could this be your night sky, as shown in Deir Bahari, which is Hatshepsut's mortuary temple, and it covers the entire ceiling all the way across the monument, and you get such scenes in the Tomb of Nabam, right here, Nabamun, rather, where you have waterfowling. You can actually see the water, the marshes, and allows you to actually create the blue color and to express the natural environment that you see on a daily basis. And it also spreads beyond Egypt and into the rest of the Mediterranean. And a little bit later in time, we see these sort of objects produced in Greece. Here is what they know as a Kerch vase, which means it's painted with pigments. And this figure in the center right here is wearing a blue garment. This is an object that I worked on several years ago in which you see this purple discoloration. This object was a white ground lekythos that was systematically smashed at a gravesite and burned. And the interaction between the Egyptian blue and the underlying white ground material led to the creation of this purple color. So everything that you see purple on this was actually once painted blue in color. So the cuprorivate mineral actually has this exceedingly special characteristic that was discovered by a colleague of mine at the British Museum, Giovanni Veri. He shined a light on an object. Actually, I was there when he first discovered this. He shined a light on an object. He had a camera that saw into the infrared, and he saw this sort of thing, which he found that the Egyptian blue has a very intense infrared response, which allows you to see very sensitively where the pigment is located spatially within a work of art. And you only need fragments of this material. Here we can't see very much Egyptian blue at all, but when we use this technique to be able to visualize it, we find it in many different areas, which gives us a very sensitive indication of where it is. And of course, Giovanni has gone on and used it to identify these pigments on some really incredible objects. These are the Elgin marbles in the British Museum. And they were thought to have been completely lost of all their polychromy, nothing left. And when he used this technique, he found these traces of blue pigment on the belt right here. And this is giving us a new sense of the extent of polychromy on ancient objects, and not only that, the extent of use of the color blue in the ancient world. During the Roman period, we start to get a slightly different take on the use of blue. In fact, Pliny, he talks about there being a tetrad of pigments that are used. Oranges, whites, blacks, and yellows, and that's it. And that's actually what we see with these portraits right here. This is a project that we're working on with the Phoebe Hearst Museum in Berkeley, trying to characterize the pigments that are on these Fayum portraits. And the way that we use the visible induced luminescence technique that Giovanni Verri came up with is trying to look at how they were using the blue color. And it's not at the forefront in these particular cases, but it fades into the background. In fact, you can see nothing on the face is Egyptian blue, but only in the background. And in this particular case here, it's used as an outline to suggest the contours of the face before the rest of the pigment was applied to it. This was considered to be the cheap pigment, the one that could be used for any dirty project that you would want to do, but it was not the one that they wanted to show as the primary color. For that, you had to turn to the indigo. And this is the only real time in antiquity that where we see the color indigo used as a pigment. In this particular case here, it's on this textile that is saturated with the pigment red lead. Painted on top, we have these features such as the bird's feathers right here, which are indigo in nature. And this is what happens in the Roman period. The interest in blue starts to die out. We have a waning in not only the use of the color, but the technology is lost, which leaves us with nothing in the Dark Ages in terms of the production of the color blue. And for that, we have to wait until the 6th century AD, when we first have the return of lapis, this time as the colorant ultramarine. This shows up at this incredibly important cave site in Bamiyan, Afghanistan, that is actually not too far away from the Badakhshan region where we saw the first lapis lazuli coming out of to be able to use in the early 3rd millennium objects. And the type of things that we see there, I should actually mention to you that these huge monumental Buddha here were the same ones that were raised by the Taliban about 10 years ago, and UNESCO has done a fantastic job of repairing these. But what we find within the cave complex here is this use of crushed lapis lazuli to produce the pigment ultramarine. And not only that, we find the first use of oil paint here as well, which is a finding that my colleagues at the Getty Conservation Institute came up with several years ago. It took about 300 years for this technology to travel from Bamiyan into the Mediterranean world, and it was primarily taken up by the Venetians, who perfected a way of being able to purify this material. And you have to understand that while you have this deep blue color, this lazurite, it's also contaminated with a lot of other things, such as whites, calcite, diopside, wollastonite, and even flecks of pyrite that are, if you were to crush this and produce a pigment, it would create an anemic gray mass rather than a vibrant blue color. So the question is, how do you remove these mineral inclusions to be able to create the vibrant blue ultramarine that we all come to know and love? Well, we're very lucky that there was a craftsman writing between 1370 and 1440, Cennino Cennini, who actually wrote down exactly the recipe for being able to do this, and we replicated it in the laboratory. Let's see if I can get this video to work for you. You take your rock from Afghanistan, you crush it into a gravel, and I still have the bruises by doing this. It's actually a very difficult rock to be able to crush. You form a powder of it, you mull it so it's only around 100 microns in size. And then through the power of alchemy, you mix it with colophony, mastic, and beeswax. And it's actually very interesting that this entire scientific thinking about this comes out of a milieu of a magic in terms of the material use. That the wax is a fire sign, and the white material is also fiery, so you would expect it to partition into that, whereas the blue that you see here can be extracted into this lye solution because it is a water sign, and so it should go into that water solution very easily, and what you're left with is a deep dark blue intense pigment. Why this works is incredible. We don't really know. In fact, that's part of our research that we're going into right now, is trying to understand this a little bit better. But here's the thing. We went from this rock to the extracted material to this much material. practically nothing. And that is why it was worth more than the price of gold, and artists read into their contracts because it ended up with such a small amount. And not only this, the church at this particular time point started to codify color symbolism, and the Virgin Mary was always painted with this blue robe onto it, so it was highly desirable to be able to use this pigment to be able to depict it in art. But artists didn't always want to pay for that much, so they tried to come up with other ways to be able to extend the pigment. So they wanted to find cheaper ways of doing it. One of the ways of doing it is to take another pigment such as azurite. Azure makes a terrible blue because it has a greeny color and it doesn't really cover your ground mass very well. But if you put a layer of this down first, as shown by this object by Pacino de Bonneguida, then you put another layer of ultramarine on the top of it, it produces these very deep blue saturated colors, and you don't need a whole lot of ultramarine to be able to do it. Another way of creating it is to create a synthetic glass. This goes back to our Bronze Age production, where you're taking a glass material mixed with cobalt to be able to create a synthetic variant of your lapis lazuli. And the reason I'm showing you this object here, it was long considered to be a fake in the British Museum, but it's been rescued from that status because we now think it's a work of the 18th century, again, meant to mimic lapis lazuli, but done in an ancient manner. But what this comes out of is pottery production. We've seen these type of pottery glazes on early Islamic pottery. In fact, this is one of the first blue and white type of wares that you see. And the cobalt colorant that you see here, this is very interesting to me from a material point of view, has almost exactly the same trace element composition as that Bronze Age glass that I showed you earlier, which suggests that while there probably is no continuity and tradition between these two groups of people, that they're using the same mineral resources to be able to create both of these objects. From here, the pottery goes into the blue and white ware that we see in China, and then from there it goes into the Delft ware, all in response to this early use of cobalt. And even goes into the Renaissance workshops of Andrea della Robbia to produce the blue background that you see here on this ceramic material. So you can take this blue pigment called smalt, crush it up, form another blue colorant, which is often used as an underlayer right here. And here we have a deep dark blue robe. We have the smalt glass that is in the layer down here, and just a thin little scumbling of the ultramarine on top of it to be able to create that blue color. And again, this is about the economy of use of these materials. Of course, this was not enough. Ultramarine is still expensive, no matter what you do. So what you have to do is find out new methods to be able to create a cheap pigment. And the way that that was done is through modern synthesis. The first synthetic pigment, blue pigment, is Prussian blue. And there's a very interesting story that's surrounding this, that it was produced out of an alchemical laboratory by a man named Johann Dippel. And Dippel was trying to find the elixir of life. And what he did is use bull's blood, and he boiled it down with potash. And this potash material, potassium carbonate, was contaminated with an iron cyanide compound that was extracted from the blood. On this other side of the laboratory, there was another guy named Diebasch. And what he was doing is trying to make a brilliant red color by crushing insects, cochineal insects, and mixing it with iron sulfate, alum, and also he needed one other ingredient, which was this potash. And when he didn't have this potash material, so he went to the other end of the laboratory, borrowed the potash that was already there, and mixed the two of them together, not knowing that it was contaminated with this iron cyanide. And what he produced is a potassium iron cyanide. And this potassium iron cyanide first turned to kind of a grayish blue, and then it got deeper dark blue color and deeper until he found that he produced a really amazing synthetic pigment out of it. One that such artists as Canaletto used to paint the skies, and continued to be used even by such artists as Picasso. And Picasso's blue period is largely a production of this Prussian blue material. About 100 years after that, we get the first ceramic blues, cobalt blues. And these were inventions in 1802 and 1805 for Thenard's blue and cerulean blue, and produced such objects as the famous Rainy Day here at the Art Institute of Chicago, and Claude Monet's La Gare Saint-Lazare. And it's important to remember that although these were created out of a ceramic industry where you're taking raw materials such as cobalt, aluminum, and heating them up to high temperatures to be able to create these pigments, they were first invented in the late Bronze Age with pottery that's like this. And then we have synthetic ultramarine. These colors that I've showed you thus far don't have the same sort of saturated blue, dark blue that was really desirable. So in 1824, the Society for the Encouragement of Industry put down a 6,000 franc award. 6,000 francs in today's money is around $50,000 to put it in perspective. And what they did is said, okay, someone go out there and produce a synthetic pigment, which shows you the power of philanthropy. And Jean-Baptiste Guimet, a chemist working there, put together these raw materials: kaolin, sodium carbonate, bitumen, and sulfur. These are raw materials that would have been extremely well understood by the ancient craftsmen. He calcined them, which means heat them up at high temperatures, and produce this blue colorant, and it's still used today. And I'm showing you this use of a contemporary artist, Laszlo Moholy-Nagy, modern artist rather, who worked out of the Bauhaus, and this is another project that we're working on with the Guggenheim Museum right now, to be able to characterize the artistic output of this very important Bauhaus artist. But what he used is this plastic material that contained this ultramarine, synthetic ultramarine pigment. He probably didn't know that ultramarine was in this object, but he liked the intense blue color and then used it to paint on. And then from the 1960s going forward, synthetic organic chemistry takes over, and then all bets are off with the ancient techniques of producing this, because they're able to do really incredible things with synthetic chemistry today. But we are still using copper as a colorant, surrounding it with a porphyrin matrix of organic molecule, producing the Bocor Magna colors that were used by such color field artists as Morris Louis in his Ware painting. I wanted to end the presentation with this right here, because I think it really brings it full circle. We have Yves Klein, who in 1957 worked with a group of chemists to be able to create his own synthetic version of ultramarine. And here we have one of his output right here, in which he wanted to take away the medium. He didn't want it saturated. He wanted it to look like the raw material. And the reason for that is he wanted to convey nature. He wanted it to show the reflectivity of the sky, the water, and all those abstracts of nature in a single painting. And I think that he conveyed that quite well. So to recap where we've been, we've seen that from the very beginning of time, lapis lazuli is used. It took around 2,000 years to be able to obtain the technology to be able to extract the blue colorant out of that lapis lazuli to produce a sustained pigment. From there, Yves Klein takes it over and uses it as an expressive force to really explain what his ideas about nature are all about. Lapis lazuli also leads us into copper-based materials. We have the first glasses that were produced in response to the need to have this blue color, which leads into the most popular blue pigment in antiquity and probably all humanity. And then we still use copper today to create organic complexes, such as in this color field painting. And finally, we have cobalt-based pigments, in which we're taking cobalt ores to be able to create pottery. These ceramic pigments are then formed into pigments much later in time. And then finally, we find it on the rainy day in Caillebott's famous painting there. And all this is to show that we have a deep connected history with the blue color. And it is something that I carry with me today, actually this understanding of the deep origins and the associations with the beginning of civilization, this particular color. It's been a true pleasure to talk with you, and I would really like to take some questions if you have them. Thank you. So if you could please wait to actually take the microphone before you ask the question. Yes, please.
Thank you very much for your talk. Could you talk about the blue in the Blue Virgin stained glass in Chartres Cathedral?
Yeah, so that's also a cobalt blue glass and came out of the same traditions of producing cobalt blue pottery. And the intense blue color that you see, all that dark blue color glass is colored with cobalt.
In the Morgan Library in New York, there are huge columns of lapis lazuli. Is it possible to mine it in such a way?
So this is part of an overall research project that I have that didn't have the opportunity to discuss, that we're looking at the origins of blue pigment from around the world. Today, we know that there are mines in Chile, in Siberia, and Afghanistan, and they're all producing large amounts of this material. So exactly where the Morgan Library material comes from, I'm not really quite sure, but we're trying to develop the analytical tools to be able to identify where it comes from.
You were mentioning that blue is rare in nature. What about sapphires and iolites and all of those blue stones, one of the most popular?
Yes, yeah, so this was part of the overall trade of semi-precious materials, but they're still rare, and people want to come with synthetic analogs, trade equivalents of the material, and that way it became an economy in its own right. So yes, those exist and they were used, but they were still out of the reach of many people, even the elite.
One place that you do see blue is flowers, even though they're unusual. And I wonder, could they not make pigments out of blue flowers of different types, or are they so rare that it wouldn't be worth doing?
So the one plant material that comes to mind is indigo, but I don't know a lot about biology, so I'm not going to answer that question very well. But here's the thing, that I've always heard that flowers are not really true blue, that they're not a chemical color, that they're more due to the interaction of light with the structure of the material. I might be wrong about that, but that's something to look at.
Okay.
If blue is such a synthetic color, how does it become a primary color?
Well, yeah, that brings up an entire idea of philosophy, and that our primary colors we have now are not the primary colors they had in antiquity. And if you take a look at I mentioned Pliny and his tetrad of colors, that it could have been an entire mixture of different systems of mixing color to be able to produce different tonalities. These portraits that we have from Tebtunis that I've been examining are really produced out of these four colors that I mentioned, and it is outside our general conception of color theory that we have today.
Can you go into some detail over the Yves Klein blue?
Where am I? Oh, the Yves Klein blue. It is ultramarine. So it's a synthetic ultramarine color, and that he was actually devising a carrier for that material. Roplex, I believe he was using, which is an organic material that would actually appear matte in appearance instead of a saturated, glossy outside surface. So the idea is that he wanted the appearance that the pigment was just applied to his canvas without having any weird way to attach it to that canvas. And the idea was to have a pure pigment. And I think Anish Kapoor picks up that theme later in his work to create those piles of raw pigment that are then tracked around all these museums that the curators and conservators have problems with.
I'm unclear on something.
Yes, please.
Cobalt is a natural blue.
Cobalt, yes,
Indigo is a natural blue plant. Lapis lazuli is a natural blue. What I've heard was that they have different applications. You don't use indigo to paint on the walls, but you do use it to dye your pants.
Yeah.
You use cobalt to make a ceramic. You use lapis to make pigments. Is that correct?
So
Are they all three natural blues?
So they actually don't exist in nature as a blue color, and that's the interesting thing about the cobalt. It's actually a pink color in this aluminum sulfate, this alum material, and that they had to convert it over through chemistry, essentially, to be able to produce the blue colorant. Indigo, again, is not blue when it first comes out. It has to be, through chemistry, manipulated to be able to produce that blue color. Lapis is the only real one that's utilized in any large amounts to produce this deep dark blue color. Yeah.
So when you were talking about the Cellini that was made the recipe, and then those portraits and the wax,
Yes.
are those the portraits that were encaustic?
So
Encaustic is the ancient use
So
of...
yeah, that's right. Those portraits that I was showing you were actually, the binding media is wax. So these are encaustic paintings in the Roman period, yes.
And what's their relationship to the blue?
So yes, I'm sorry that I wasn't clear on that. So the blue that's used there is merely to tint the background of those objects, or to be used as an underdrawing to guide the painting that was out on top of it. And it wasn't used as a color in its own right, but merely something to create a tonality. The wax is, well, that's another interesting idea, is that typically speaking, these wax were impregnated with lead white. And lead white actually causes a dispersion where you can't see through the wax as well. The painting techniques of fine portraits is absolutely fascinating. That's another one of these topics that I'm a little bit obsessed by.
Maybe a half-crazed question, but is blue more radioactive?
No, not that I know of. It has no reactivity that is associated
So
with
is it maybe then only in the glazes that are used?
So,
Because-
I mean, you can have natural radioactivity, but none of the materials that I was presenting actually have any radioactivity as far as I know.
Have you looked into the caves of Mogao in Dunhuang in China? Because when I was there, I was told that the blue on the walls was really lapis lazuli that was painted on the walls.
Yeah, I would love to have an opportunity to go take a look at those pigments. And I've also heard the same thing, that these early Buddhist sites were where lapis lazuli was used again in a sustained manner to be able to create these pigments. These ones in Bamiyan are the example I chose to show you. But yes, Mogao would be a great example of that.
And also when I was there, they told me that those caves that have green on the wall are from malachite, and you can tell what happened with the trade patterns depending on what color they used at what time.
Absolutely.
Could you please speak about the blue in the Madonna's robes in tempera art, say, of Duccio or Giotto, and also in fresco?
So yes, those are all ultramarine pigment, and this was the Cennino's recipe of being able to extract out all those other mineral inclusions to be able to create this really intense blue colorant. So Duccio was using ultramarine to be able to create those frescoes. So maybe a couple more questions?
Professor,
Yes.
where are your blue suede shoes?
That's a great question. I'm going to have to look into that.
I know this is probably a really long question to ask,
Sure.
but I'm curious, in some of these pieces that you're showing, their traces of blue are so slight and so small. How do you go about sort of collecting a sample to analyze without also compromising the art that you're looking at?
You know, this is a fantastic question. I really thank you for asking it. We spend a lot of time discussing this very subject about how do you take a sample and should you take a sample of some of these objects. Sometimes there's not enough material. Sometimes the surface is so pristine that you don't want to take a sample. And these are decisions that are weighed not only with the scientists, but the conservator and the curators that are looking at the work of art. And it's a case-by-case basis. And sometimes you know that the information that you're going to get from that pigment extraction is going to be well worth you taking it. And other times you say, it's not really the right time to be able to do that. So yes, this is at the foremost of our thoughts every time we go in to take a sample from a work of art. We do it very deliberately. Thank you.